Well, thinking a little bit more about 3D seismic now, I showed this to you yesterday, where you can use seismic attributes, as we call them, to highlight geological features. And one that is very easy to highlight is using the curvature of a horizon, and where you might have curvature like this, where you have an antiform structure and then a synform structure here, so that your seismic wave, when it reflects off the high area, the antiform, the waves spread out, and when the seismic waves hit the synform, they tend to converge rather than diverge. And you can mathematically determine the amount of curvature and make maps like this 3D seismic map of the surface of a horizon in a fluvial system, and it really highlights the channel very well. In this case, here's your outline of your channel. This is called the most positive curvature, and it's where you have your waves diverging over a topographic high, like you would get on the channel margins. So what you've really shown here are the two margins of a channel, very nicely displayed with this seismic attribute. Down here is what we call a most negative curvature. Most negative curvature. The first one that I showed, most positive curvature, that's this one here, and most negative curvature down here. And so your the feature that you see most prominently is that one there. And if you were to pick that up and put an overlay onto the most positive curvature, you would it would fit quite nicely in there. So what you're doing is you're getting an expression of a channel. In this case, there is a meander bend here, right about in this position here. So you've probably got a nice point bar deposit kind of right in that area. So using these attributes, and there's a lot of them, one of the professors that I work with, Dr. Marford, he wrote the book on seismic attributes, and he has, I don't know how many different seismic, they're mathematical manipulations of the seismic data, of the raw data, and he has developed, him and his students have developed many algorithms to get better displays of features, usually on seismic horizon slices, but also vertically. Okay, well, let's look at some examples now this is one that a colleague of mine, also in the same department with me, a guy by the name of Matt Pranter, and what he did was a combined field outcrop subsurface study. And the object of his study was to study this gas field that's called the Rulison field, and it produces gas from the Upper Cretaceous, a formation called the William Fork Formation, at depths of about 6,000 to 9,000 feet. And it's a very complex reservoir, so to get a better idea of the reservoir, he went first to some outcrops of the same formation, the Williams Fork Formation that produces gas in the subsurface. And so he studied the outcrops. This is a map of Colorado, and we're up in this area here, and here's an enlargement of that. The Rulison Field is again a gas field that occurs right about in an area like this, where you have very nice outcrops. These gray areas here are all outcrops, and a lot of those outcrops are of the Williams Fork Formation that makes up the reservoir in the subsurface. So what you see here is an outcrop analog to what is in the subsurface. And what he was able to find in the outcrop was two intervals. One, which a lower sand, he called it, a lower sand from about this position to that position, and then an upper sand. Okay, and what he found was the sands were quite different. The lower sand tended to be very low net to gross, and it was thought, after studying the outcrop, determined that it was meandering river deposit on a coastal plain setting. The upper part, okay, above that line, this is a well log from the Rulison Field. So based on the outcrops, determined that the lower sand was a meandering river deposit with a very low net to gross, or net sand. In the upper part was a high net to gross and interpreted as a braided river deposit on an alluvial plain setting. So much more sand up in this upper part, much less sand down in the lower part. And that was determined also not only from the field, but also from looking at the outcrops. So you've got a low net sand down here with just a few sands, as you can see, in predominantly a shaly system. And then you've got a high net to gross here, dominantly sand in this upper interval. Well, they were very lucky there in that the outcrops in this area are three-dimensional outcrops. They are in canyons, and here, for example, is an aerial photograph of a canyon, and you can walk down this canyon, and the walls of the canyon are the Williams Fork Formation, the same as the reservoir. And then that canyon makes a right angle bend, so now you can see a different view of the reservoir at of the sands at right angles to this part of the canyon. So what they did was, so here's a cartoon showing that, where you have the Williams Fork Formation exposed on the canyon walls here, and then you make a right angle bend and you see the same thing but at a right angle orientation. What they did is they measured a lot of stratigraphic sections. All these lines here are measured stratigraphic sections on both sides of the canyon wall. And because he had stratigraphic sections oriented this way and then oriented that way, it was just like getting a three-dimensional image. So again, all of these lines are measured stratigraphic sections along the walls of the canyon. Well, if you, so he mapped all of these and built a stratigraphic model, and if you now take this bend in the channel and you kind of flatten it out, so you're in 2 dimensions now, this was the picture that you get, where you, the vertical axis is thickness, horizontal axis is distance, and this line right here is where you have that bend in the canyon, right about there. So all of these measured sections here were measured at this orientation, and all of the measured sections here were taken at that orientation and just flattened out. So the black here are sand bodies. This is mainly in the lower part, I believe, in the lower low net to gross interval. So you can see that there's a lot of different sand bodies kind of isolated within, these are point bar deposits, isolated within that stratigraphic interval that you measured on outcrop. Well, one of the parameters, if you're building a geological model, one of the parameters that you want to put into that model is the dimensions of sand bodies. And that's what Frander did. He actually measured the thickness of beds of 668, or let's see, what is this, 683 or something sand beds. That many individual beds, he measured the thickness. They call it apparent thickness. Excuse me, well, apparent width, same, yeah, apparent width, not thickness, but the apparent width, because it's apparent rather than true width, because sometimes you were at an angle that was not perfectly perpendicular to the outcrop in the canyon walls. So it's an apparent thickness, width, and then he measured the thicknesses. So the average apparent width was 365 feet wide for these channels. And here's the thickness, the width measurements. And then the thickness part, the average thickness was 12.1 feet. Okay, so that gave you a ratio of width to thickness. Now, width, thickness is something you can measure on a log. What you can't measure on the well log is the distance or the width. Okay, so to account for that, if you've got a well log database, and there was no seismic associated with this one, so this is more of a well log interpretation. But if you go to an outcrop that is similar to what you think your reservoir is, you can do these same sorts of measurements, your width versus thickness. And when you do that, in this particular case, in the canyon walls here, the Williams Fork Formation, here's thickness on the vertical axis and the apparent width on the horizontal axis. And what you can do then is you can kind of average out. You see a trend there, and here's kind of an average trend line. Now this is a logarithmic plot, arithmetic on the thickness scale, but logarithmic on the width scale. So this is the plot from that 600 and however many it is, I can't really read it, 683 or something like that. So now you can go to this plot And for example, let's say you have a bed that's 20 feet thick that you measure from your well log. Okay, 20 feet thick. Go to that trend line. So the apparent width for a 20-foot thick bed would be about, because this is a logarithmic scale, it's about 600 feet wide. Okay, so you've got a ratio of 600 width to 20 feet thickness, so a ratio of 3 to 1. 30 to 1, excuse me. 30 to 1. Yeah. Yeah, 30 to 1. Well, that's so. At any rate, now you've got something that you can put into when you're building your model. You can put in the width because you have the thickness data from your well log. Well, however, there's a little issue there in that the issue is that you've got quite a wide spread here of thickness data for any given. Excuse me, you've got quite a variability in your width for any given thickness. And so really, you could say that for a bed that is 20 feet thick, the minimum thickness is going to be 200, the minimum width will be 200 feet, and the maximum width will be 1,200 feet, with an average width of 600. Okay, so now that's kind of a drawback because now you've got quite a wide range. And what you would do is in your geological model building, you would run a number of iterations with different thickness to width ratios and put into your model then ultimately the iteration that you think most closely resembles your reservoir. So that's how you can build thicknesses of sand bodies or dimensions, widths and thicknesses when you have well log data. And in this case, a good database of width that was from measurements from an outcrop. So then he was able to apply this data to building a geological model in the Williamsburg field. You had a question?
What's the meaning of multi-story and single story?
Is of what?
What's the meaning of multi-story and single story in the graphic on the left?
The legend.
The legend.
This?
No.
The bottom right one.
This.
In that
right.
plot,
What is apparent width?
No.
No.
What's the meaning of the multi-story?
Okay, all right. Multi-story is where you have a number of individual sand bodies that are stacked on each other. A single story is where you just have one sand body, okay? And then down here is splay, those splay deposits that I pointed out before. So multi-story, really, they call it channel, but it really refers to the point bars, where you might have a set of point bars with the lateral accretion and everything. Whereas a single one, you might just have one set of lateral accretion beds, for example. So that's the difference. Okay, well, so that allows you to start to build your model. Here's that data now as kind of generalized for that same multi-story channels, single-story channels, and splays, and also amalgamated channels. I'm not quite sure what they meant by that because that really is quite similar to multi-story channels. But at any rate, here's little pictures of what is meant by these. The multi-story, in this case, you've got 2 layers here. A lower layer, that's 1 story, And then another layer that's in the second story. So that's a multi-story sand body, and it has a mean thickness of 70.9 feet and a mean width of almost 6,400 feet. We get down here to our single or our multi-story, and mean thickness is 16.2, mean width is 517, and it's a single story because you've only got one set of the point bar deposits. Down here, the single story channels are going to be even thinner, 10.7 feet average thickness, and the width 336 feet. And then the splay deposits are the thinnest ones of all, mean thickness of 3.2 feet and mean width of 228 feet. So again, it goes back to understanding the type of deposit that you've got, because the properties, the reservoir properties, in this case, the shape is going to be different depending upon the method of deposition. And this is going to affect your porosity and your permeability as well, even though it's not shown in this diagram. So one can take a data set like this, and if you think, for example, your reservoir is similar to the Williams Fork outcrop, you might be able to use this sort of a trend line or the range to make your calculations of width and thickness. So a very important parameter that you can best get from outcrops, particularly that width parameter. You get that from your outcrops. Okay, another example. This is a fluvial deposit, a point bar, multiple point bar deposit in oil sands in Canada, Athabasca oil sands from Canada. And this was in a publication in, I think it was 2010, I think that says. Well, whatever. I think it was published in the AAPG Bulletin in 2010, I think it was. Because this is a oil sand, a heavy oil sand. Typically in heavy oil sands, you have to drill a lot of closely spaced wells, and you do, in this particular case, you inject steam down some of the wells that lowers the viscosity of the oil, and so the oil will flow to a well bore. So you typically have to drill a lot of wells. And you can see that here, well there, well there, well there, well there, and so on. Now, this is it's kind of hard to see, but this picture here is a seismic horizon slice. And the first thing you can see is meander bends. There's a bend, meander bend there. Another big one right in here. Another one right there, another one over here, and so on. There's several of these. In fact, here's a cartoon showing the point bars and the channel. This is Cretaceous age, so the channels are in the subsurface, and obviously, have been mud filled. So how can you detect if you've got mud filling or not in your channels? Well, one way to do that is just use a gamma ray log, and that's what was done here. So the colors here that you see, greater than 100 API units, is dark brown, and that's going to be shale. So you see a lot of these abandoned channels are in fact shale filled. Here's one that's completely shale filled. Another one that's almost entirely shale filled. And so to get this heavy oil out, you're going to have to do a lot of closely spaced drilling. Here's another cartoon showing the abandoned channels here. And the little scroll marks here indicating the lateral accretion packages. So, in this particular case, your abandoned channels that are mud filled, one there, one there, another one there. And so, for example, if these are mud filled, which they are, they give you a high gamma ray when you drill into them, then you're not going to get any connectivity, for example, between this nice point bar deposit and this one up here or that one over there. Okay? They're all going to be isolated. How did you determine that on well logs? Well, you just looked at the gamma log, and your highest gamma ray API units represent mud, and so that's how that was determined. Ideally, you would not want to drill into a mud plug, but a lot of these wells were drilled before the seismic was shot, and so there were wells that actually did penetrate the mud plugs. They were not good reservoir, not good wells. Well, the different rock types that you see, there's 4 different rock types.
Excuse me.
4 different rock types.
Mister,
Yeah.
in the last slide, please, in the seismic, you can see the seal or the shale that you are.
Well, yeah.
Because that was my last question before, that the seal is atomic in the fluvial system.
Yeah, see, these are going to see what you're looking at here is where a lot of wells have been drilled, okay, and so they with the gamma ray log, where you had your high gamma ray, that would represent shale seal, and so you see one there, one there. These are all these mud plugs, okay, that you can determine as to because they have a high API gamma ray. So does that answer your question, or you're still thinking above that?
No, it's okay.
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 And you can see that, you can see these, you can see the meander loops there. So you know where your sand's going to be. In this case, you know where your sand's going to be, where you know where your mud plugs are going to be, because you can kind of see the channels that are now abandoned and filled with mud. And so again, you use one of these horizontal slices in order to see the reservoir horizon in all its complexities. Well, there's 4 different rock types, and I show you pictures of 3 of them. This is rock type A, is your reservoir, and you can see it's black colored, it's good sand, black colored because of the oil, and it's the main reservoir facies. But you also get, on occasion, another facies, or rock type, which is called a mudstone class brecciated sandstone. And what that really means is it's a sandstone with some big shale clasts in it. And that's this rock type B. And then rock type C is this one here, which is interbedded sandstone and siltstone. So the sand is light colored, the silt is dark colored. So those are the three facies, and the main one, based on the core, is this nice, massive-looking sand that is very heavily oil-stained. Now, if you're working in marine deposits, you've got a distinct advantage in that marine deposits normally have a lot of fossils associated with them that you can use for correlation and for age dating and things like that. But in non-marine environments, you don't have that large number of organisms. So is there anything you can use for correlation? Is there any biological thing that you could use for correlation or for age dating and things like that? And the answer to that is yes, there is. And the science of these non-marine organic material is called palynology. And the organic material is pollen and spores from trees. Like I'm still in this Cretaceous example, there were a lot of trees, so pollen and spores indicate a non-marine environment of deposition if you find those in your core. And in this particular case, there were pollen and spores indicating a terrestrial or non-marine source, but there was also a marine organism called a dinoflagellate, which that organism lives in a low salinity marine environment, like as you would find in an estuary or a nearshore marine environment. Here's just some pictures of what they look like, these organisms. I've got a better picture in the next one to show you. But these are what the pollen and spores look like. And here's color pictures of what they look like. Different sorts of pollen and spores. And I don't think there's any dinoflagellates in these pictures. Not sure. But you can use them for correlation purposes and for age dating, because different types of trees, for example, live during different geological periods. And so if you find the pollen and the spores from those particular trees, then of a certain age, then you have been able to use the pollen to age date the timing of deposition of the sediment that contains the pores and spores and pollen. Similarly, you can determine how much of a marine influence you had and how much of a non-marine influence you had in deposition of the sediment, because there you can just do a look at ratios between the pollens and spores versus the dinoflagellates, which are marine. So you can get an idea of how much marine influence you had, if any, by doing the palynology. By doing the palynology. Okay, well at this point, up to this point, I've been talking about just descriptive features of sand bodies, or meandering river sand bodies. Now I want to start to put this into the context of geological time. And I've got a whole lecture on this for later this week, but I'm just going to introduce the topic of sequence stratigraphy to you now, which is really the time aspect of stratigraphy. When strata are deposited, what geological time are they deposited, both in absolute terms as well as during formations like a Cretaceous age formation or what have you. So let me show this picture first. That here's a shoreline today, okay? So you got your marine environment down here. Here's your shoreline, nice sandy beach, sand dunes behind the beach, and some muddy lagoonal deposits behind that. But that only represents today, an instant in geological time. What happens, though, is that through geological time periods, the oceans expand and contract. When they expand, we call that a marine transgression. And during marine transgression, if your sea is expanding, you're going to have a landward migration of the shoreline, say from this point today to progressively further in the landward direction with time. If your oceans are contracting, getting smaller, you're going to have just the opposite. Your shoreline is going to what we call regress or regression. Your shoreline is going to migrate in the seaward direction because you're contracting the ocean, the volume of the ocean water. So your shoreline responds to that and moves seaward. So with geological time, we know from a lot of study and all, we know that through geological time, we have had these series of transgressions and regressions. And we call these cycles, sea level cycles, where the marine environment transgresses and then regresses. What happens when you get these transgressions or regressions? During transgression, for example, what will happen is you'll have your initial shoreline right here, and with transgression, your shoreline migrates up to a point like this. So what are you doing? You're adding marine waters. Your transgressing seas are covering up sediment that was deposited prior to the origination of the transgression. During regression, just the opposite occurs. Sea level falls, and so you might go from this position down to that position, okay? And when that occurs, you get erosion. When this area now becomes exposed to the land, as the shoreline moves seaward, you get erosion here. So during regression, you get erosion. Then with a period of transgression, you'll get deposition. In the next period of regression, you'll get erosion of that material that was deposited during the preceding transgression, and so on. Now, the other thing that happens is that when you're transgressing or regressing your shoreline, particularly when you're transgressing your shoreline, this is kind of like a high energy surf zone here, okay? Here's the picture. You have a nice high energy surf zone right there. And so as the shoreline migrates in the landward direction or transgresses, you get this very high energy zone moving in the landward direction, and it will erode away all or part of the material here that was deposited, let's excuse me, I said that backwards. Yeah, excuse me, I said that backwards. Well, let's see now, I don't want to complicate this. Yeah, during transgression, you can get this high energy shoreline that's going to erode sediment that was deposited during a previous change in sea level. I'll leave it, that's a little more complicated with that, but I'll leave that for now. So one of the things that happens is when you drop your sea level and you get that erosion occurs and it forms a surface. And we call that a regressive surface of erosion due to a drop in your sea level. Or an RSE, as it's sometimes called, regressive surface of erosion. Another term that I'll get to later is sequence boundary. Unconformity is another term that's used to define this surface of erosion during the falling stage of sea level. And during the rising stage of sea level, if you've got a nice high energy surf zone, for example, you can also get some erosion. And we call that surface a transgressive surface of erosion. It forms when sea level is rising. Okay? So the important thing is that you get, when sea level changes, you get these surfaces of erosion or due to transgression or due to regression. Well, we can express that in terms of geological time. So let me go to this diagram. And here we have an interval of geological time on our horizontal axis. Our vertical axis, you see the word high and the word low here, and that refers to where sea level is. If it's a high stand of sea level, you're getting transgression. So your sea surface or sea level is rising. If you've got regression, where the shoreline is contracting or moving seaward, that's when you get a low period of where your shoreline is. Shoreline moves seaward here, and it moves landward over there at this part. So, at any rate, you have in the vertical axis the change in sea level, and it's usually cyclical. So you get a low stand, a high stand, another low stand, a high stand, low stand, high stand, over an interval of geological time. So here's just one, what we call a sea level cycle. A single sea level cycle where we'll just start out randomly where you have a high stand of sea level, and now the shoreline moves seaward. We have then some turnaround point, and the shoreline then is moving landward. I wish I was a better drawer, but I'm not. So I have all these wavy lines that aren't supposed to be that way. But let me redraw that. So we have high sea level here. The shoreline is going to be way landward. Now we start a cycle where we drop sea level, meaning the shoreline is going to move seaward till we reach this low stand of sea level, then turn around, and now we're going to start to transgress, and our shoreline is going to migrate in the landward direction. So over this particular interval of time, whatever it is, 1,000 years, 1,000,000 years, whatever, you've had this cyclic change in sea level, which is going to affect the type of deposit that you have and the type of erosion that you have. Let me explain that a little bit better, I hope. Some of these are kind of hard concepts to explain. So here we have our falling stage of sea level, turnaround stage, then our rising stage of sea level. So here the shoreline is moving seaward, shoreline moving landward on that limb of this curve. So now I can explain this picture that I passed over. On the falling stage of sea level, kind of the area shown on this sea level curve, the area shown by this blue rectangle, your shoreline is going to be in this upper corner here. Your shoreline will be way out here. Low sea level, you expose the continental shelf area. You generate valleys here by river down-cutting valleys, and sediment that is brought to these valleys ends up in the deep ocean as a submarine fan deposit. By contrast now, when you go up the cycle and raise sea level, your shoreline now is in a position something like this. So your shoreline is moved from this position way out here to this position during that sea level cycle. So during the high stand of sea level, you're going to get deposition of sediments, like maybe a delta or something, or shoreline deposits. But during the low stand of sea level, when this area is going to be severely exposed, and so you get erosion here. One of the features of erosion is what we call an incised valley. And what that means is during a low stand of sea level, your rivers coming down are going to be able to move across the exposed continental shelf and carve out a valley. Then when you raise sea level, marine waters will come into this valley and turn it into an estuary, a marine estuary, so you'll fill the valley with sand and mud. So the position of your shoreline is very important as to determining where you're going to get erosion, where you're going to get deposition. You're going to get erosion when you're landward of the shoreline, and you're going to get deposition when you're seaward of the shoreline. If that's complicated, it'll be less so as we go along, because I'm going to start using the sequence stratigraphy and the things that I talk about. So at any rate, that is kind of sequence stratigraphy, changes in the stratigraphy as a function of geological time. And with time, the shoreline moves landward, moves seaward, landward, seaward, landward, seaward, and so on. Well, the sediments that are deposited during this time, we call those a sequence. And we'll define it here as a stratigraphic unit composed of a relatively conformable succession of strata that are related. and the succession is bounded at the top and the base, down to the top and base, by unconformities. We'll just leave it at that, unconformities. So, a depositional sequence is a set of rocks or strata deposited during one sea level cycle. Here you have
I have a question.
yeah.
Is there a relation between sequential and cyclic stratigraphy?
Sequential stratigraphy?
Yeah,
It's the same thing.
it's the same sequential and cyclic stratigraphy.
Yeah. Sequential would mean that deposition and erosion occur sequentially over time. The sequence stratigraphy is the same thing. It's the strata. It's the study of the strata that occurs over time. That strata is deposited sequentially. Okay. So, a depositional sequence, here's a sequence of rocks shown in yellow. They're going to be bounded at the bottom by an unconformity or an erosion surface, or if you want to call it a sequence boundary. And it's also going to be bounded at the top. In this case, the lower unit is going to be one of those transgressive surfaces of erosion that I just defined. And this one at the top will be a regressive surface of erosion. Okay? So they both give you erosion surfaces, but at different stages of sea level. So once again, at the falling, starting with a high stand, right here, a high stand where your shoreline is in a landward direction. And then as you drop sea level, your shoreline moves out towards the left here. And by the time you get to this turnaround point, your shoreline is now migrated here from where it was earlier. So what goes on in that area then is during high stand time you get deposition, during low stand time you get erosion up here. Now it's different in deep water deposits, but we're not worried about those now. Okay, so full rise cycle, that's what it looks like, and I'll be referring to it quite a few times from now on, which is why I wanted to introduce this topic now. That fall rise occurs over an interval of geological time. Okay, well, the reason I wanted to bring that topic up is because what I want to talk about now are another type of a fluvial system called an incised valley, valley fill, and reservoirs, because these incised valleys, fills, are quite common in the geological record, and they make for very good reservoirs. What you're looking at here is a modern day incised valley. Here's a river coming down this valley, and it ends up in the ocean. Here's the shoreline out here, and all of this is a surf zone here. Okay, so a nice high energy zone right at the shoreline. The valley was incised into during a period of low sea level, when this river was very energetic. Okay, so it could do a lot of carving out. So it carved out this valley. It's like this picture I showed you this picture here, where you get during the low stand in sea level, you get an exposed continental shelf because your shoreline is now way out here, and so you create or you carve out these valleys. So during the falling stage of sea level, the valleys are formed, they're eroded out during a falling sea level. During the rising sea level and at high stand, those valleys become filled with sediment. And so that's one of the, and so what you end up getting in this area is an incised valley that has been filled during, the valley was carved during a drop in sea level and then filled during the following rise in sea level. Well, actually, the cycles and the sediments are a little more complex than that explanation, but we'll get into the complexities later on. All right, so here we are back. This is a modern day incised valley. You see it's subarrially exposed, so the river is probably pretty energetic and can, over geological time, can carve out this valley. So this valley was carved out during a fall in sea level. Here's the shoreline here. During the next transgression, the shoreline is going to move landward, and because you have this high energy surf zone here, all of these sediments that are deposited in the valley can be, all or part of them, can be eroded away. Okay? So here's a little cartoon that kind of illustrates that, where you have a modern day river, and the valley walls here and there. And in this case, during the filling of this valley, the valley was carved during the falling stage of sea level, and then in filling, that occurred in a number of stages, and you actually had different types of fluvial deposits forming in that incised valley. So these yellow are point bar deposits. For a period of time, your channel was over here, depositing a point bar, and then the channel migrated, say, somewhere like this, and over time, and deposited another point bar, and then the channel moved over here and deposited another point bar. So what you end up in these incised valley fill deposits is that they can be very discontinuous reservoirs. Lens-like reservoirs that are discontinuous. They form during the rise in sea level when you backfill the valleys that were carved out during the previous low stand of sea level. And they've got all the same features. They often have all the same features of meandering rivers, except they're confined to a valley here. But sometimes you can get river deposits here as well. I'll show you some examples of that probably this afternoon. So, 3 different sand bodies forming in this incised valley fill. All right, well, let's see how, if you have a valley, say a valley, and let's go through a sea level cycle and see how one period of time where you have one fluvial system deposited, how that would occur. So what you see here, if you can read the bottom here, we have what we call here a low stand fluvial lag that's colored in green. Well, during the falling stage of sea level, you see here on my curve, that's when you carved out this valley, during the falling stage of sea level. When sea level started to turn around, you deposited some nice coarse grained, what are called here aggradational fluvial deposits, fluvial sands, and they're shown in red here. As sea level rises, what's going to happen to your incised valley? Eventually, marine waters, as sea level rises, the marine waters are going to finger into the valley, turning it into a estuary, saline water estuary, and you then have estuarian sediments. First maybe estuarian sand, shown in yellow, and then maybe estuarian muds, shown in the light brown here. So this would be a typical fill. Now, if sea level kept rising after that, then you'll get marine mudstone deposited on top. So what you end up with is a very nice top seal, a side seal here, and a side seal over there with your nice sandy fill in here. And that sandy fill, ideally, is going to have fluvial deposits at the base and grade upward into estuarian deposits, and then up into open marine shelf deposits. So that would be the typical vertical stratigraphy that you would find in one of these incised valley systems. Let me take about a 5 or 10 minute break just to stretch and get your blood flowing a little bit. Nobody wants to take a break?